Welcome to section 1.8. We're going to transition, as we've talked about systems of linear equations, to introduce a new idea. And this actually is going to take us a little bit into chapter 2, but this is a very important idea in linear algebra. It's something called transformations, specifically linear transformations. So in this section, we're going to talk about what are linear transformations. We're going to do some examples. Then we're going to talk some more about transformations in general. So let's start off with what are transformations? Well, a transformation is a function or mapping that goes from one Rn, so it takes a vector with n components, and takes it to being a vector with m components. So this is you may have heard of these as terms of functions. They don't necessarily have to be functions, but they kind of do follow the rules of functions. They're also called a mapping. Now, transformation is the term that we use the most often in linear algebra. Now, to add to this, it's a rule that assigns each vector a vector in my new space. Again, we haven't defined vector spaces, but it gets the general idea that we will again come back and talk about this a little bit more. The starting set, so just to make this even more clear, our Rn, which is where we are starting, is our domain. Now, it's very much what you are accustomed to. You're used to probably normal functions where x is your domain. So actually, your domain is usually the real numbers. It's everything you can plug in. And since by definition of transformation, we can plug in everything in the Rn. However, Rm is called the codomain. I'll get to range in a little bit. So this idea is actually a critical difference, and perhaps maybe you learned in some other classes. So in this situation, Rm, which is where we are going, is the codomain, because we are not necessarily going to hit all of Rm. We may not. In fact, let's just talk about individuals. If I have a specific vector, the image of it is t of x. In other words, where did that x vector end up? And then the set of all those images is the range. So this is an idea that you have actually dealt with before and maybe not fully understood, because you've always talked about domain and range, but domain and codomain is actually a bigger thing in linear algebra, because we're talking about the general areas in which worlds we're playing in, universes, whatever you want to think about. These are the spaces we're working in. Whether or not we actually hit everything in there is a different question. In fact, that's a more advanced class where we talk about different kinds of functions, if they are one-to-one and onto and so forth. Not going to go into that in this class. But we use the notation where t, semicolon, Rn, arrow, Rm. So always we have we use t for transformation, but technically we can use any, and it's usually used a capital letter. We have our domain where we start and our codomain where we end up. Hence the arrow telling us the directionality in it's going. All right, so these are some basic terminology. Well, let's add to this by talking about linear transformations. These are actually the most important transformations. A transformation is linear, so it's one of those functions that goes Rm to Rm if it meets two requirements, namely that the sum of vectors, that the image of that is equal to the sum of the images. And the image of a scalar of a vector is a scalar times the image. In other words, it preserves scalar multiplication and vector or matrix addition. Because technically, while we're talking about this in terms of Rn to Rm, this idea actually expands and then starts talking about a little bit more in terms of we can actually do this on matrices, and it gets kind of interesting at that point in time. But so we want you can combine both these properties, and sometimes you Google, they say it's a linear transformation if it preserves simply all of this. Because this, if you notice, is just a combination where I have two scalar coefficients. So I'm pulling the scalars out while I'm also breaking up the addition. Now, the reason I don't focus on that is because it becomes harder to diagnose what is the problem. So it's easier to focus on one addition or scalar multiplication at a time. Now, another key thing to point out on this is that, again, these are the most important class of transformations in all of linear algebra because it's linear algebra. So linear transformations is a very, very classic question in linear algebra that we want to understand. Now, let me demonstrate this by doing an example. So example one, I have a transformation that goes from R2, so I have two values I'm inputting, and it's going to R as defined by, it's going to take the square root of the first term squared plus the second term squared. So to demonstrate this, let's just look at a single value. Let's let t, let's execute that on the vector 2, -1. By the way, you may recognize this as the distance formula. So what this is it's going to take this, and it literally will make it the square root of 2 squared plus -1 squared, which is the square root of 4 plus 1, or the square root of 5. Boom, we did that. All right, question number 2. Now that we've done an example to see how the transformation worked, is this linear or not? So this is actually asking us to go back and think about those two properties. Does this preserve scalar multiplication, and does it preserve addition? If either one fails, period, then this fails. And I'm going to demonstrate that actually both will fail, but you don't have to do both of them to fail. So first, let's look at scalar multiplication. Now notice, I am doing this in general. I am not using one specific example. Because you could pick an example that this may happen to work, but that doesn't guarantee it will always work. We are solving this in generality. We are doing a little bit of abstraction to verify that this will always work, because you may happen to pick the 1, 200 examples where it may work. Heck, it could work for 1,000,000 examples. If there's even one where it fails, then it's not linear. So we literally, so I'm going to make a note over here. Pardon, I just clicked on that. Let's go back just 1 second. So C of V is really C times the vector. I got V1 and V2. So this is C, this is going to be the vector. Remember, by scalar multiplication, C of V1, C of V2. Hence, when we plugged it in, we got C of V1 and C of V2. Now, when we square, we know how to distribute our squares. So I got this. Now, continuing on this, you can factor a C squared out of both those terms. And so we have C squared times the sum of V1 squared plus V2 squared. Now, by our square root properties, so again, notice we are using all your algebraic skills from your past. Yes, you need to know algebra. We actually use that in linear algebra. So we now apply that, and when we take it out, now here's a key thing. Some of you may have forgotten that the square root, I'm going to write this down, the square root of any value squared is the absolute value of that, because square roots always give me a positive. So in this particular case, if C had been a negative, I get the absolute value, which is not the same thing as C. If C had been -1, you could just even do the example where C is -1, and you quickly realize order of operations, I get that absolute value, which is something you should have learned in one of your previous algebra classes. Because of that absolute value, it's not equal to the original thing, and therefore it's not, notice, so therefore this is not equal to C times that transformation of that vector. So this alone tells us it's not linear. That enough, we could stop right there. But I want to demonstrate this a step further to really illustrate this and make sure you can see both different versions. So let's consider the summation. Well, again, what is that summation going to be? Let me change colors just to make this a little more explicit. This would literally be V1, V2 added to U1, U2. So when I add those together, I'm going to get the new vector V1 plus U1 and V2 plus U2. So if I plug those in, I would get this, V1 plus U1 squared. Now, here's an important thing. If you wanted to multiply this all the way out, you would end up with the square root of V1 squared plus 2V1 U1 plus U2 squared plus U1 squared plus V2 squared plus 2 times V2 U2. Well, notice I want this essentially to be equal to the sum of their squares. So that would be the square root of V1 squared, U2 squared, and U1, U2 squared. This whole thing is not equal to that. First off, even if I didn't have these two terms which muck it up, even if I didn't have those, you can't break up a square root by summations, hence it's not linear. So all we have to do is break it. By the way, breaking it, if you find one example where it breaks, then you can use an example. It's called a counterexample. But if we don't know if it is linear or not, I don't recommend using an example, because if you pick an example and it works, that doesn't tell you anything. So you have to pick another example. Still works, doesn't tell me anything. Pick another one, still works, doesn't tell me anything. So we want to solve this in generality. All right, that's the end of this example. Come back for example 2, where we look at a different transformation and continue talking about this.